Okay, welcome everyone to our April Tech Talk. It's being hosted by NUFAB. We're going to get going. Just a few things. If you have questions, feel free to put them in the chat, and Suwon and Sirkan will be checking that and probably answering your questions at the end of the talk. Okay. Suwon, you want to start?
Yep. Okay. Thank you for the coming. Today's talk, Tech Talk, title Enabling Microfluidics at NUFAB. My name is Suhan Choi. I'm a postdoc at Nuance NUFAB, and Sirkan, he is the research engineer here at NUFAB. Okay, today we are introducing what is microfluidics and why we use it, and what type of microfluidics, and then what's going to be the application for that technology. And mostly we are introducing what kind of method here at NUFAB to provide for fabricating microfluidic devices. So we're going to introduce 3 different microfabrication microfluidic molding. So SU8 and then laser cutter and DRIE. So yeah, what is microfluidics? Microfluidics is the study of fluid flow and the design of the components that are geometrically constrained to especially a micro scale, where the surface forces are dominant than volumetric forces. So microfluidics has an interdisciplinary field such as engineering, physics, chemistry, biology, material science, and environmental engineering, and food science. There are lots of different areas people utilize microfluidics. And in microfluidics, small length scale, what that means, it does have like different physics comparing to macro scale. One of the example is capillary reaction. So when we look at this cartoon, 4 different sides of the liquid droplet, and the diameter for the bigger one, let's set 1D, and then the small one is 0.1, and smaller one is 0.01, and then the smallest one is 0.001. The corresponding surface area, let's say the bigger one is 1A, and this small one is 10 to the minus 2, and 10 to the minus 4, and 10 to the minus 6. What about the volume? Is 1V for the bigger one, and then 10 to the minus 3, 10 to the minus 6, 10 to the minus 9. And for the weight, 1 kilogram for the bigger one, and then 1 gram for the small, and smaller is 1 milligram, and then the smallest is 1 microgram. So I just want to compare surface versus volume. So when we compare surface versus volume for each different size, then the bigger one is 1, and the small one is 10, smaller one is 100, and the smallest one is 1,000. What it means that comparing the forces, like gravitational force versus surface tension force. Surface tension force is a lot dominant when we have like a smaller scale. So by using that kind of physical phenomena, we can utilize microfluidics. So one example is capillary reactions. When you see this image, it shows multiple different sizes of the tube. The bigger one is the macro scale, but when it goes to the right-hand side, the size of the capillary tube is getting increased, so that the capillary is getting increased. It's because surface force are more dominant than the gravity. That's the reason why it's getting higher. Why microfluidics? it has low sample volume required, so we can reduce the cost. And parallelizations, we get like high throughput experimentation, and it has like a small physical, so we get like an economic footprint. And for the smaller physical, so we can make the batch fabrication, and it gives us a quantitative benefit, and definitely automation. It's compact version. So the advantage of microfluidics is lab on a chip. So lab work is going to be inside of the single chip. Let's introduce what type of microfluidic devices. So we have like 4 different types, and I want to start continuous flows microfluidics. That's more general types of microfluidics, and then it manipulates liquid flow through the fabricated microchannel without breaking continuity. So mostly people are using syringe pump, or even pressure-based pump that can push the liquid through the microchannel. And a variety of applications include micro nano particle separator and particle forcing, chemical separations, and there are lots of different applications. And a second one is Droplet-based microfluidics. That's the manipulate discrete volume of fluid in immersible phase with low Reynolds number and laminar flow region. So in microfluidics, it's gonna be low Reynolds numbers because constrained size of the tube, or even like a channel that gives us low Reynolds number. And then it's gonna be a laminar flow. So we cannot reach turbulent flow in microfluidics. That's huge advantages. If we have like turbulent flow, then there are lots of eddy motions that's gonna prevent lots of laminar kind of flow, so that we cannot do any kind of this video like reagent addition and droplet encapsulation and droplet sorting. And micro droplets allow for handling miniature volume, like a microliter down to femtoliter. And it provides better mixing, encapsulation, sorting, sensing, and the high throughput experiment. And it requires a deep understanding of droplet dynamics. And third one is digital microfluidics. It is an advanced fluid handling technology, and that precisely manipulate individual droplets on substrate by using electrowetting. So electrowetting refers to the ability of applied voltage to modulate the wettability of surface. So simply saying, by applying the voltage, we can modify the localized surface tension, so that we can changing like one side of the liquid wettability, so that there are contact angle difference, which brings Laplace pressure difference, so that it's gonna drive the droplet from one to the other direction. And this microfluidics harness electrowetting to control droplet, as I described. And electrical signals are applied to an array of electrode to define the size and then the position of each droplet. So when we see the video, the smaller and large size of the square electrode, that's the individual electrode. And there are an array of electrodes, so that we can define the size and then the position. And it moved by turning on and off the voltage in adjacent electrodes, so that we can bring dispense and transport and merging and mixing and that kind of sequence, we can do it. And paper-based microfluidics. one of the example is the pregnancy tester, which is one of the paper-based microfluidic applications. And the paper-based microfluidics rely on the phenomenon of the capillary penetration in porous media. So people are using the paper and then making it hydrophobic and hydrophilic. So the hydrophobic is kind of the barrier, so that the liquid only penetrating within the hydrophilic area. So as we can see here in the procedure, we have the paper, and then the papers can be coated with a certain type of hydrophobic. So here in the case, people use the PDMS because PDMS are naturally hydrophobic. But there are a lot of different materials like Cytop or fluoropel or Teflon AF we can use as an hydrophobic layer. And then the paper sandwich with a hydrophilic chromatographic paper, so that it's going to be the only working within these chromatographic papers. And another example is glucose detection, which is also one application of my paper-based microfluidics. Okay, to do the microfluidic fabrication, we should know the photolithography. So I'm going to introduce a little bit about that. For the procedure, we have the substrate, and then we have the some kind of hard material on top of that, and then we applied photoresist by doing the spin coating, and then we use the mask aligner by using a certain type of mask. So we have a chromium mask and then iron oxide mask here in NUFAB, and we expose the light by using contact aligner, and we develop and then etching with RIE or wet etching, and then stripping the photoresist, and we can make the photolithography work for the microfluidic fabrications. And required tools are mask aligner, and substrate, and photoresist, developers, and spinners. And here at NUFAB, we have two different aligners. The top, we have SUS MJB4 and MABA6 contact aligner. And we have at the bottom Heidelberg Micro PG501 and MLA 150 maskless aligner. So whenever users came here, they can utilize this one. So basically, mask aligner, people can make the mask, and then by the mask, people are using the contact aligner to do the multiple patterning. And microfabrication for the microfluidic mold, we just want to introduce three different methods by using SU8, and another one is laser ablation and deep RIE etching. So like SU8 and deep RIE, we just use photolithography to make the patterning, and then we make the mold, and then we use PDMS molding, and then we use the glass as a cover. A deep RIE is the same kind of similar procedure. We use photolithography, and then we just etching to make the mold, and then make the PDMS microfluidics. And the laser etching, we can directly etching on top of the silicon wafer to make the mold. And SU8 properties, it has pros and cons. SU8 is permanent epoxy resist, so it's very chemically and physically stable, and we can make wide range of thickness, and it does have a high aspect ratio. Whereas there is an cons, it's impossible to remove once we make it cross-linking. Then it's almost impossible to remove it. And if we want to make quite large thickness of the SU8, and it's kind of exhausting working because it take a number of times and multiple different stage, like spin coating multiple times, and then the pre-baking multiple times, things like that. And it's difficult film stress control. What it means, it's gonna easily crack it, especially around the edge. If we make like a kind of a sharp edge, it easily crack it. So for this case, we have to do like hard baking to compensate it. And the adhesion is poor, so sometimes on top of the silicon oxide, it's not well adhesion. And some of the mold fabricated here in NUFAB, we use SU8 mold as a microfluidic channel. And then at the bottom, the cartoon image is made by Zygo. So whenever users want to make the kind of 3D mapping, then they can do it by using Zygo. Okay, I'm gonna toss to Serkan about the rest of the presentation.
All right, hello everyone. Let me share the rest of the presentation. All right, so I'm going to take from here and talk about how we use the DRIE. Oops, one. All right, so how we use the deep RIE to make the silicon molds for PDMS casting. And then I'll talk about the new kid on the block, our laser ablation machine, which is highly productive if you need to do some basic microfluiding with microfluidic devices with large feature sizes. All right. Now, NUFAB's deep RIE, you can see it here on the screen on the image. It has this famous Bosch process, which is an alternating etch and passivation cycles. It costs a lot of money to have this license, so we will be very happy if you come and use it. What happens is that it etches for a certain amount of time using fluorine chemistry in the chamber with ICP coupling, and then we passivate the edges of the features with some sort of Teflon coating. Then we switch back to the etch process. This way we can achieve very high aspect ratio patterns, as you can see over here. You can I mean the possibilities are endless here. These things are like over 300 micron deep and 10 micron wide. Pillars are easy. Well, it's not very easy, but you can use it to achieve these kind of high aspect ratio structures, if especially you need to make some intricate microfluidic devices. It makes very like almost perfect 90-degree straight sidewall. The high anisotropy is how we can achieve this high aspect ratios. We can do nanometric size features too, if you are interested in that that like nanofluidic type of stuff. But you can do on the order of millimeters or centimeter devices as well. It's a highly automated machine. It has a load lock. We put the substrate in, and we just send it in, and it will finish the recipe for us, and then we'll take it out. All right. So it's a very nice machine, but you will have to do the lithography as Suhan mentioned in the beginning. But the nice thing about this method is that we use standard positive photoresist, which has high resolution and very easy to work with compared to SU8. And and that lithography step will take you, if you're an experienced user, at most half an hour, I would say, and then you can easily etch your pattern into the silicon mold. That way you can have a very robust mold. All right. So here are some example devices we made. So this one on the top left is a microfluidic device etched into silicon. You can see there are very thin walls between the microfluidic channels, which would be very difficult to attain with SU8, but with DRIE, we can easily make it. Here is a little SEM image on the bottom left. You can see like 90-degree wall profile of these pillars. So these are like 1:2 aspect ratio. It's not that high as in the previous images, but we easily achieve like more than 10 aspect ratio in the DRIE before, and you can see it actually here. So on the right hand side, you can see the images, top images of these. So these are kind of like traps. They are embedded in the microfluidic channels. They're supposed to catch some particles for further analysis. So the particles in the liquid carried through these traps, and then they will be catched in these openings, and then some like confocal microscopy or whatever you can think of, you can do that later. So these opening between these two pillars, these fancy shaped pillars, are about 2 to 3 micron, and we achieved like almost 30 micron deep holes to make the PDMS casting with these things. All right, next. There's also a bonus feature of the DRIE, which is the PTFE deposition. So PTFE is a general name for Teflon-like polymers. So they are really like non-stick surface coating material. When you, especially when you have high aspect ratio patterns in your mold, it is very difficult to peel the PDMS off without ripping it apart, because if you have like a small hole and small deep holes, the PDMS tend to stick in that and rips off when we remove the rest of the PDMS. So you would need a specific like a chemical treatment. That's what typically reported on the papers. So it's called like silanation process. And so it's it's time costly. You have to pay for the chemicals and things like that. So it's not everybody has access to those of things. But if you use DRIE to coat this PTFE material, this is the stuff that we use for the passivation. Your surface will be extremely non-stick and hydrophobic. And we got very good feedback from users when they use this material on their molds, and they can easily peel off their high aspect ratio patterns from the surface. So it's very effective. And it's not specific to DRIE too. Even if you make your mold with SU8 or the laser ablation, which will be coming in a minute, you can still put it in the DRIE chamber and just coat it with this PTFE material. That way you'll get a nice mold. All right, now our laser ablation machine called LPKF-R Proto Laser. This is the new kid on the block, as I was saying. So it has a very short spot size, considering it's a laser. It's not technically microfabrication, but it's in between microfabrication and like fabrication in the machine shop, like using drill bits and stuff. So it's you can make stuff down to 15 micron here. But the nice thing about this one is it doesn't require lithography. You just draw your pattern using your favorite CAD software and just bring it here, and it will machine it into your substrate. It can be anything really. We used different materials in the past, like silicon is the most common one, obviously. We can machine into glass slides. We can machine into steel sheets, or any kind of metal or polymers. That's pretty common in the lab. So people use flexible polymers as their microfluidic devices, and they cut it with this laser cutter. All right, so let's next one. All right, so how we do this? So it has this focused laser beam. It's a very high intensity laser. As soon as it strikes on the surface, it creates a very hot plasma, which expand the gas around it. That expansion creates a shock wave. That shock wave breaks off material, and the material kind of ablates off from the surface. So that's how we go deeper and deeper. Due to the physics of light focusing, the laser focusing, we end up with the slightly tapered edges, and since it's a physical fabrication, we have slightly rough surface behind. But For some applications, this is still acceptable. You can cast your PDMS on here and make your device that way. But if this bottom surface roughness is a problem, we offer another type of operation. You can get certain thickness of substrates. You can get silicon in various different thicknesses. So let's say you need 200 micron deep channels. You can get a 200 micron thick silicon, and you do your cuts all the way through with the laser, and then you can bond this piece onto another brand new shiny surface silicon wafer, and this way you can use it as a mold, which will have perfect surfaces top and bottom, and it will seal better than the first case. Right, so that's another way to do that. So, here are some examples, the things we have done. So this is making the grooves on a substrate without cutting it all the way through. So these grooves are made with the laser. So these like microfluidic channels here. And, you can kind of see the cross section on a glass piece. What is the side angle and things like this. Is a very deep hole, by the way. So you can see the scale bar is 200 micron over here. So it's almost like 0.5 millimeter deep into the glass slide. So you can achieve very high aspect ratio microfluidic channels with this method as well. But if you wanna cut something else, so this is an alumina device cut out of a sheet of alumina, and you can bond this thing onto a piece of silicon wafer. Most users just use double-sided tape. You can put the double-sided tape back before you cut this piece, for example, and then once you cut it, the double-sided tape will be cut as well, and you can just peel the backing off and then stick this onto another substrate, and you'll have your microfluidic mold very easily. And you can even achieve like a 10 micron gap at the bottom of these things. So it's very very powerful method. All right, so we introduced you 3 different methods, using SU8, using DRIE to make the molds, or using the laser cut. But you should know when should you choose which one. All right. Personally, I don't like to use SU8 at all, but SU8 is very effective in this region. On the bottom axis you have your channel depth and channel width on the vertical axis. So if you have small features, small channel widths and channel depths, SU8 is still very good and useful, and it's kind of easy to work with around this region. But as it gets thicker, it gets really, really trickier to use, and you need to time your curing a lot more better than it's less forgiving, I should say, because of the different stress on the film, on the SU8 film during curing, so it gets cracks and things like that. So I wouldn't really suggest any users to go beyond 100 micron. It gets really, really tedious. In contrast, the DRIE is very versatile. If you have access to it, you can use it for almost anything. For deep structures, thick silicon wafers usually cost quite a bit more than standard 0.5 millimeter silicon wafers. So that's one thing to consider. But in general, it's your best bet if you need to go anything beyond 100 micron. And the laser cutter is kind of fits in this region a little bit. You can make really small features with it, but if you are after large area things, you can use it. One other thing you can use it is for, like, sometimes people use 3-dimensional, sort of semi 3-dimensional microfluidics. So they have like 2D microfluidic, and then they have like connection channels from one point to another. So you can do that with LPKF easily on a piece of glass slide, for example. So when you bond your PDMS onto a glass slide, you'll have like transfer channels within the glass as well. So that's another method to use it. All right. We prepared a little table for you. What you should expect in terms of like trainings or what you can do. So you can see the like feature sizes and aspect ratios that are kind of easily attainable. But in terms of effort, I would say SU8 is most effort requiring method. So you will need to be careful about a lot of things. There is a lot of room for errors. And especially new users gets very frustrated when they start using SU8 as their first photoresist for photolithography. So there's that. LPKF is kind of the least effort required machine. You just draw your pattern in a AutoCAD, mostly what people use, and then bring it over, load it to the machine, and it will start cutting. That's what it is. With the deep array, I'd say it fits in between, because lithography for deep array is a lot easier than dealing with SU8, but you have the deep array step to finish, which is, since the machine is automated, it's not very cumbersome. And so to produce the same mold, assuming that you can use all three to make it, you will. So these numbers are for like experienced users, by the way. So you typically require, you need to do 3 hours of active work, including photomask making with SU8. Let's say for 25 to 30 micron thick SU8 films. If it gets any thicker than 50 micron, it will get quite longer. For example, Suhan is currently making like a 500 micron thick SU8 films, and he's curing them 2 to 3 days, and developing takes 24 hours. It's just it can get exponentially higher as the thickness goes up. With LPKF, you just need to load your substrate and start the cutting. Depending on the material, cutting may take quite long. Sometimes people leave it overnight, but you don't have to be there, so that's a plus. So you just need to be at the machine for a little bit of time, and then it will do the rest for you. And with the deep RIE, typically you would need about 1.5 hour active time for even with half a millimeter deep channels. And you obviously would need some tools to get trained on. So the SU8 is, like I say, most demanding. You will need MLA 150 for your mask making. You will need acid bench training, because you will need to etch your mask with acids. And then you obviously need SU8 spinner training and the contact aligner training. You can order your masks. We can do it for you. So, you can drop these 2 trainings if necessary, but I suggest you just get trained on it, because, you will need to change your mask a lot down the line. And, if you know how to make a mask, it will make your life a lot easier. So typically you would need all 4 of these things to be able to work with SU8. With LPKF, you just need LPKF, and with the deep RIE, the addition of spinner and the deep RIE would be needed to finish the work. All right, so that's about it for this talk. In conclusion, you can use microfluidics for high throughput, quantitative, small scale benefits for like a lot of different applications. A lot of like medical students are coming to us, and we do fabricate microfluidic devices for them, or sometimes they get trained and they do their work here. So it's a very nice opportunity to have here in NUFAB at Northwestern. And we have a lot of tools that makes it possible. Virtually, you can make any kind of microfluidic device you can think of. We have other support tools as well if you need different dielectric coatings or electrical contacts. You can do that here at NUFAB too for complicated microfluidic devices. And we are working hard here to serve you better. So we welcome you all the time. And feel free to contact us for any kind of your microfabrication or nanofabrication needs. And with that, I'd like to thank you all for coming, and we are open for questions.
Looks like there's a question in the chat.
Let me see. Okay, so there's the question is how could you please comment on how fast laser cutter can generate structures? That would depend on the depth and the length you're cutting or area you're cutting. It can do 2 different types of cuts. It can cut like contour lines. So in that case, it will be limited by the length of the total cut. And if you're making an area etch, like a hatch type of cut, then it will scale with the area you're cutting, obviously. So on silicon, for example, if we want to cut out a 500 micron thick silicon wafer fully for like 5 by 5 millimeter square out of the silicon wafer, it takes roughly 5 minutes. So you can kind of extrapolate it. All right. So let's say, so 5 by 5 millimeter square is what, a 20 millimeter long cut. And that would take 5 minutes. So I would say it's in the 1 millimeter, well, what is it? 5 millimeter, 4 millimeter per minute is for silicon. It highly depends on the substrate you are cutting. So if it's polymer, for example, it's a lot faster than silicon. In general, like inorganic materials like ceramics and stuff cuts slower than polymers. But yeah, you're looking for some, it could be like 15 minutes to 6 hours. That piece I showed, the alumina piece in the presentation, took about 6 hours to cut. But the alumina is by far the hardest material we cut so far. So. Multi-layer, okay. Do you offer multi-layer microfluidic device fabrication? Do you have experience integrating valves? All right. What kind of valves are we talking about? Is it like external things, or we do have syringe pumps and stuff like that, but well, I mean, you can do multi-layer microfluidic devices. It is possible. We never done it here that I remember. Nobody has done it, but you can mix and match the different pinch of valve. Maybe Suhan can comment on this a little bit better because he has more experience in microfluidic area. But in terms of multi-layer fabrication, we can mix and match different methods. We can make a mold on silicon, and then we can etch into glass, and then that way we will have like a some routes going from one place to the other, and that way it could be doable.
Okay, I can take over the question. The internal valves, it depends on what type of microfluidic we're gonna do it. For the the droplet types of microfluidic in flow focusing device, then we can introduce two different liquids so that we can pinch off the droplet to generate it. It depends on the a different flow rate of the different continuous versus dispersed phase. Then we can make the pinching off. Or if we want to use like a electrowetting based digital microfluidics, then we can manipulate by using electric electrode pattern, and then we can actually do it like pinching off, even like without the valve we can manipulate the different droplet. So yeah, it pretty much depends. And for the internal valve and also like channel types microfluidics, we can make capillary valve inside of it, and then also we can apply that capillary valve underneath the valve. We can also apply certain electrodes so that we can make the valve. It's possible. Yeah, I don't know that to what you are asking or not, but yeah, basically I can say yeah, it's possible.
Does anyone have any more questions? Okay, if not, thank you for attending. Oh, wait, there's one more question.
Yes, we do. Yeah, we can assist you with any kind of design, and we usually offer users, so they come up with some paper they read online somewhere, and we just go over it and we see what we can do. If we can perfectly replicate what's what's being reported, and we can do that, but we usually offer them better ways to do stuff, considering our capabilities and things like that. So yeah, we always do that, and we can like arrange like Zoom meetings, and everything goes with it. And we are happy to do so.
Okay, thanks everyone for attending, and stay tuned for May's Tech Talk coming up. If you have any other questions for Serkan and Suwan, you can go to our website, our NUFAB's website, and find their contact information there. Okay, thank you.
All right. Bye,
Bye,
everyone.
thank you.
Thanks for
Thank you.
coming.
Bye, everyone.